Hi guys, hope you're fine and doing well. So today we will be discussing this problem from the LeetCode, which is all possible full binary trees. So this is the 14th problem of the dynamic programming series. If you haven't watched the previous videos, you can consider watching them since it will be really helpful for you to understand the concepts in the upcoming videos. And if you're new to this channel, you can consider subscribing it and giving thumbs up to this video. So let's get started with the question. So the question tries to say that we are given an integer n and we have to return a list of all possible full binary trees with n nodes. So what is a full binary tree? It's a tree basically which has either whose parent has either 0 children or exactly 2 children. And what kind of output are we supposed to return? So this is the kind of output that we are supposed to return. So this is first confirmation of the binary tree, and this is the second one, and similarly all other. So what does this signify? So this signify that this is the root, and for this root it has 2 children, and in case it has 2 children, then those children will be represented as 0, and in case it has no children, so they will be represented as null. And for this parent, it has these 2 children which are null, so it means that there are no children for this parent. And for this parent, these it has these two as the children, and similar because they are null, so they can't be parent. So for this parent, it has these two as the children basically, which is null and null again, and it won't be possible. And for this parent, these two are the children, right? So this is what this array means. Now let's consider that we are given an integer n is equal to 7. So with the n is equal to 7, how many full binary trees are possible? So let's consider this case. So this is the first case that is possible. And if we detach, wait a second, yes, and if we detach this part and attach it here, then this will be the available confirmation to us. And if we detach this part and attach it here, so this is the another confirmation possible. And the next is if we detach this part from here and attach it here or here, basically we have two options, so these two will come out to be the other confirmations. So here we understand that either a parent can have 0 children or 2 children. So here are only two ways possible for each node. So each node has only two options. And so now let's have a look at the constraints. So the constraints for this problem are, for the worst case, it is 20. So if we clearly see that the complexity of this time complexity of this problem will be something of 2 to the power 20 if we try it in a brute force manner, right? So if we do this, it will come out to be 10 to the power 6, almost 10 to the power 6. And since we know that we can do 10 to the power 8 operations in 1 second, so this brute force will also work. But the main question arises is that why we will be using dynamic programming and how can we reduce the time complexity for it. So let's have a look at it. So now let's consider that we are given n is equal to 4. And if this n is 4, now let's try that how many full binary trees are possible for this number of nodes. So first we create a root node, and for it we give it two parents. And now if we see that only one node is left, so we cannot attach this one node like this because this is not a full binary tree, because the definition says that each parent can have either 0 children or exactly 2 children. So this parent does not have exactly 2 children. And similarly for the case of n is equal to 2, when we have two nodes, again this is the same case, that this is also not a full binary tree. So from these we can observe that and conclude that for whenever we are given n, so to answer and output the total number of full binary trees, we should always have number of nodes as odd. If we have even, then it won't be possible to make it full binary tree on the first place, right? And the other thing that we observe is that the cases where are we able to make full binary trees, then the total number of nodes in the left subtree are also odd and in the right subtree are also odd. We can confirm this in all these cases, right? So now let's have a look at how can we approach to this problem. So let me just minimize this. So let's consider we are given n equal to 5, and for n equal to 1, this is the only confirmation possible, which is the single, and for n equal to 3, this is the only confirmation possible, right? So for this 5, if we have to make confirmations for when we are given 5 nodes, then what all possibilities are there? That if we have this node, then we can attach for here the answer for n equal to 1, or we can here attach the answers for n equal to 3. This will give us the confirmation of one of the confirmations for 5. So let's see how is this possible. That here we have root node, and here we will connect for n equal to 1, which is only single node. So we connect this here, and here for n is equal to 3, we have this confirmation. If we attach this confirmation here, right? So this is one of the possibilities, and answers for n equal to 5. So this will contribute to the first answer. And similarly, the other possibility is for n equal to 5, here n equal to 3's answer can be put, and here n equal to 1 answer be put here. So what will it result into? For n equal to 3, it will give something like this. So this part is for n is equal to 3. This is the answer for that. And if we attach for n is equal to 1, which is this one. So this is the other possible confirmation. So these are the two possible confirmations for n equal to 5. So here we can think it like this, that we can break our problem into some sub problems. That for n is equal to 5, 1 will be the root node, and the rest left out nodes will be 4 nodes, right? And now this 4 can be broken into 1 comma 3 or 3 comma 1, right? So this is how we can break this into subproblems. And similarly, if the case was for n equal to 7, then how could we break it? One node will be the root node, and the left out nodes will be 6. So it will be 1 comma 5. So we will attach in the left subtree. So the left part of this bracket represents that this is the answer for left subtree, and this will be the answer for the right subtree. So one of the possible is 1 comma 5, and the other possible is 5 comma 1, and the other possible is 3 comma 3. And if we further notice one thing, that for this part, so let me clear this. Yes. So this part, it is basically, if we say that it is something like 1, so 1 is in the left subtree of the root, which is again 1, and The rest 5 can also be divided into again 1 and 3. So comes out to be 4 and 1 is for the parent. So this is how this 5 can also be made. And the other possibility of making this 5 is, so basically this is the left subtree and this is whole the right subtree, and in this right subtree this is the left part and this is the right part and this is the parent. And the other possibility for this is that 1 and now 3 will come in the left subtree, 1 will go to the right subtree, and again the 1 will be for the parent. So this is how these 5 nodes will be arranged. So here we can see that these are basically the two conformations for 5. So if we clearly observe the right subtree, these are these two conformations, and similar is the case for this. So it will come out to be 1 comma 3 in the left subtree and 1 will be the parent, and for the right subtree it will be 1. So the case that will be possible is 3 and 1 in the left subtree. So basically what we are trying to do is we are just trying to add this part and this part. Like for n equal to 7, this will be the root node, and if we add for n equal to 5, we can directly attach this part here, and the other possibility is we can attach this part in its place, and here for n is equal to 1, which is again 1 only, single node. So here also two confirmations are possible, here also two confirmations are possible, and for this n equal to 3, this is the only one that's possible. So this is only one, and if we just add up them it will come out to be 5. So total for n is equal to 7, we have 5 confirmations for the different types of full binary trees available to us. So let's look how can we think of code. Let me just clear this out. So if these are the n nodes that are given to us, and here the n is 7, what we will try is that firstly if we want to make this part as a parent, so basically the root, if we make this node as the root, so what all nodes that will be in the left subtree and what will be in the right subtree. So these set of nodes will be in the left subtree and these set of nodes will be in right subtree. So basically these are 3 nodes, and here also these are 3 nodes. Basically what we need here is n is equal to 3. We will attach the answer for this left part and we will attach the answer for this right part. And similarly if we were making, let me just change the color. Yes, now if we were trying to make this as a root node, so what would have been the possibility? This would have been in the left subtree and these set of nodes would have been in the right subtree. So the answer would have something look like n is equal to 1, and then we have attached all the confirmations for n equal to 5 here, right? So this is what we did just previously, like how can we attach these. So these are all the confirmations that are possible, so we will just iterate over all the indices of these nodes, and then we will try to make each node as the root node. And then we will look out that for each particular node, how many confirmations of the full binary tree are possible. So like for this part, there are X confirmations available, for this Y, Z, and similarly so on. So we will just add them all up, and then we will get the total number of formations that we can make for the full binary tree where n is equal to 7. So now let's have a look at the code. So how we are required to output is, we are just required to output the list of all these root nodes. Basically, all these nodes. We have just to return their addresses and in the form of a list, and the function on the backend will simply iterate over all the indices. Like if we are given these set of confirmations, and like these are the three set of confirmations that are possible for particular n, then we have to return this node, and this node, and the function at the backend will simply just iterate over all the nodes for these particular root nodes and print the answer in the form of this for single confirmation, right? So now let's have a look at it. So firstly, we will be making new function wherein we will be returning list of type tree node, and I'll call this function as function. And what we will do next is, for the base case, the base case is that if n is equal to 1, so if n is equal to 1, we can just attach that 1 in only this form, right? So we'll just create a list tree node list equal to array list. So if n is equal to 1, what we will do is we will simply add 0 here, which is the single node, and we'll return this list. Or else, if n is not equal to 1, what we will do is we'll just iterate over I equal to 1 and I is less than n and I plus plus. So one thing that we should notice here is that since we observed that the total number of nodes in the left subtree are always odd and in the right subtree are also odd. So if we try to make, for example, this node as the root node, this won't be possible because here for the left subtree there are two nodes and for the right subtree there are four nodes, which are basically even number of nodes. So we observed that there should be odd number of nodes in the left subtree and as well as in the right subtree. So we can just make these set of alternative nodes as the root. So for the answer for these part will just be 0. So we won't be adding them. So if here I should be 0, if I percent 2 is equal to 1, then only we will be performing these operations, since when for here I is 0, here I is 1, and for it 2. So if we try to make this node as the root node for the full binary tree, this won't be possible, and similar is the case for this too. So that is what we are doing here. Now here we will create a list of type tree node, and this is L, which means left, and it will contain answer to basically the left subtree, and we will create another list for the right subtree, which is R, and the total is n minus I minus 1, right? So now what we will do is, since we have all the confirmations for the left subtree and all the confirmations for the right subtree, then the total number of confirmations for this particular node that we are iterating is, like if we are standing on this node, right? So for this node, it will have answer for this subtree, and it will have answer for this subtree. Got it? And let the answer for this be 5 for the left subtree, and the answer be 3 for the right subtree. So now if we want to calculate the answer for this particular tree, what we will do is, for each confirmation, we will just explore all the 3 confirmations for each confirmation, and similarly it will go on for each node that we have in the left subtrees, right? So we will simply, it will not be n, it will be L dot size, which is size of this list, and we will just increase it, and similarly for k is equal to 0 and k is less than r dot size, k plus plus. Now we will create a new tree node, which is node is equal to new tree node, and we will just name it to 0, and then what we will do is, we will just add node dot left is equal to L dot get j. We are getting it from the left subtree, and node dot right is equal to R dot get k from the right subtree, and we will add this node this node to the list. Oh, 1 second. Yes, this is what we are required to do, and we will now simply return this list. So let's see if this is working. Oh, I forgot to return our function. Now let's see if it is working. So here we have done something wrong, that is, we have to create new tree node is equal to new tree node which has value 0, and then we are required to add this node. Yes, so yes, this is working fine, and now let's try to submit it. So it is getting submitted, but the issue here is that, let me just write these things again. So this is basically the brute force that we did, and if we want to increase the time complexity, sorry, decrease the time complexity, then if we have these set of nodes with us, now what we are doing is, when we are standing at this particular node, so we have answer for this, and we will be calculating answer for this, and when this function will be called, so what it will do is, it will further divide these 4 nodes. It has 4 nodes, sorry, it should have 5. Yes, so it will further divide these 5 nodes into same problem, and now the problem will again be reduced to, it will have to just calculate for these 3 and then this one, and then again when we call this right part, what will it do is, it will simply divided into these two parts, right? This is the one case. And now when we move to this particular part, what will it do is it will, let me write these all nodes again. Yes, and we are standing at this fourth node. So yes, if we see that this right subtree, so this will again divide it into left subtree, right subtree, and this is the parent. So when we were at the this index, it was again calculating this part, and when we are at this index, it is still dividing into this part and calculating this again. So this is increasing the time complexity. So now let's see how can we reduce the time complexity. So for this, what we will do is we will simply just create a hash map. And what will this hash map store is it will store key as an integer, and then it will store a list of tree node as the value, and we will name this hash map as dp. So here let's just pass this hash map, and now what we will check is we'll simply check if this dp contains key for the ith index, which is basically n, then we will simply return dp dot get of n, and here we will simply just write dp as another parameter to the function, and now we will just put for this n this list. Right, so we have done this part, and now let's see. Currently it is faster than 34%. Now let's see how is it impacting our answer. Yes, so now it has become quite fast. So this is how we can optimize our approach and apply dynamic programming to this question. So I hope you understood the solution to this video. And if you appreciate my work, you can consider subscribing to this channel and giving like to this video. So let's meet in the next video. Till then, bye bye.